Yeah, good morning,
Okay.
sir.
Okay. That's fine.
So
So,
he taught me at undergrad. So he's one of my teachers. He taught
wow.
me operational research. Eventually,
Wow.
I found myself here in Southampton in the Department of Operational Research as an assistant professor.
Oh, Prof. Oshinuga, we want to appreciate you for giving us Dr. mentoring Dr. Jolaoso. We are really glad and proud of you, sir.
Thank you very much, sir.
Yes, sir.
I'm really very grateful and I'm happy to be part of you.
Thank you, Prof. We are grateful. Your product
Um,
is a world-class product. Thank you, sir.
I'm so happy. Thanks a lot,
Yes, sir.
Professor Keke.
Thank you,
God bless you.
uh,
Thank you, sir.
okay, I'll try to see if I could just manage a little time to finish this slide before it goes off again. I think we have 40 minutes thereabout
Yeah.
to before it goes off. So yeah, I think we stopped here the last time. We're trying to look at what makes up a good step size for a gradient descent algorithm. And I said from the result we have, it says that if we pick our step size between 0 and 2 over L, where L is Lipschitz constant of f, then the algorithm will converge to a solution of the
Yeah,
problem.
Dr. Jolaoso, you can share your slide.
Oh, sorry,
Yeah,
I'm
you
not
can share
sure.
your
I
slide.
thought I've done that.
Okay.
Um, okay. All right, can you see my slide now,
Yes,
please?
we can see it. We can see it very clear. We can see it.
Yeah, so this is the first result proved several years ago that this condition here holds for the algorithm to converge to a solution of the problem. However, there is a problem in the sense that it's not always the case we'll be able to approximate what is the value of L, what is the value of L in this particular case. So that takes us to how do we know what other method for selecting the step size, which we'll come into. And also looking at the types of function, the second result says that if the function is strongly convex, that is like the case I mentioned, this is for the case where f is convex. But in the case where f is strongly convex, then if we choose size interval of 0 and then 2 over L plus mu, where mu is a parameter of the strong convexity of the function, and then the algorithm will converge. So this is among the results we have the existence result or the fundamental results in this area of research. Now coming back to how do you select the step size, most especially in the case where we don't have the Lipschitz constant being known. So one of the first method is by guess, which is not practical. Like we have, okay, I know if I choose 0 or between alpha k between 0 and 2 over L. So let's suppose L equals to 1. So if I choose between 0 and 2, I will always have a convergence. But what if I don't know what is L? If it's very large, then it means I'll have a very small selected value of a very small choice of value to pick from. So in that case, it might be difficult to know what is the most appropriate step size to have the algorithm to convert, because one of the aim we have in mind is we want the algorithm to converge. So yes, of course. Otherwise, the algorithm will just keep iterating without converging. So one of the way to go about this is what I call this backtracking line search or the Amidian line search. There are several types of line search, but in this case here, one of the fundamental is the Amidian line search. So it says that if we set this condition in such a way that alpha k satisfy this condition, then we are guaranteed that the step size we have chosen is a good step size, which will make the algorithm to converge. And also another our choice of the step size by a self-adaptive means. That is, we update the step size at every iterate by using the previous or the memory iterate. Like here we have alpha k being updated by the choice of sk and sk minus 1. So if we set alpha k to be equals to this, yeah, then we will have a good step size that will make our algorithm to converge. Then the other one is this here that says that if alpha k is the mean of this, if you set alpha k as this value, then we always have our algorithm being converging. So these are results in existence. Though we still have work going in this direction, we'll try to see, okay, depending on the type of function we are dealing with, if we could have a better performance of the algorithm, looking at the types of function we are dealing with. So yeah, this end the talk about the fundamentals of optimization. Going to key aspects of nonlinear optimization problems. Like I said, on my own area of research, for some years focuses on nonlinear optimization problem. So we have some key of them, which is the composite optimization problem. From the F, we have on the other case, how do we break it into composite functions, either functions of 2 or 3 or more functions, and we'll be able to have, in terms of its application, does it really make sense in terms of modeling? And as far as our model inclusion problem, variational inequality, and equilibrium problem, we look into these 3 together and see how if time permits, we'll be able to cover everything. So coming to the composite optimization problem, like in the other case, we're talking about the function f. So here, the function f has been broken into 2. So we have one of the f being smooth and the other function being non-smooth in the particular case. And also, in some case, depending on the problem you are dealing with, it can also be that one of the functions is convex and the other is not convex, or you have both being non-convex. So depending on what we are dealing with. As well as though the smoothness part is key, is very important. So it can also be a non-smooth function entirely. How do you deal with that? So maybe the 2 functions are non-smooth. How do you deal with that? All these properties will determine the method you use to solve the optimization problem. So in this case, I just break it into 2. We have one smooth, the other non-smooth. So which means that I know for the case that is non-smooth, I can't differentiate that part. So how do I deal with that part I cannot differentiate? So that comes about the proximal operator, because the proximal operator deals it's effective in terms of solving optimization problem with non-smooth problem and non-smooth functions. So in this case, I can deal with the non-smooth part, which is the G, with the proximal operator, and I have my F, which is differentiable. I can take the derivative of that. So all this is telling us, though this is also called fall backward method, because the fourth case is the case where I have this F being taking a step in the direction of the solution, while the backward case is a proximal operator, which the way it's been defined, it can be defined as the inverse of a particular function. That's why I call it backward case. So this, we call it proximal gradient method, works very well, most especially for non-smooth function. In the case where you have one being, for a composite function where you have one part being smooth and the other part being non-smooth. So there we have results that has been improve on this. How do you improve the performance of this of this algorithm? So here comes the FISTA, which is the faster version of proximal gradient algorithm by adding a parameter, a memory parameter as well. So this is just this is an extra FISTA, a form of the extra FISTA in particular, because we have the momentum function being taken to accelerate the iterates. So you have results on these that prove the convergence of this method as well. Yeah, I think I'm being a little bit fast now, but I'll try to see if I can just give as much as I can the key information in most of these slides here. Now, going a little bit from the composite optimization problem to the monotone inclusion. So how do you formulate a monotone inclusion problem? as an optimization problem, or how do you formulate an optimization problem as a monotone inclusion problem? And this goes from what I call the first optimality condition of the optimization problem. And by the other point, I say is that the function, I say that a point is a solution of the optimization problem if this point, if the gradient of the function at point x is equal to 0. So this takes us to the monotone inclusion. You have, because we have a non-smooth function, then we'll be dealing with a set in this case now, not just not a particular point, but a set of points. So this point x and x star, we can say x is a solution of this problem if it satisfies this condition, because its inclusion here, because this function g is non-smooth. And as if you can recall, to talk about some properties that we'll be dealing with next, we discussed about some the convexity property. If you have to drop the convexity property, can we build a similitude of it in such a way that we can be able to apply the idea from the minimization to the monotone inclusion? Here is the monotone, and here is the inclusion problem, sorry. Yeah, I've not seen if it is monotone or not. But the word monotone will come into play from the convexity, because monotonicity is just trying to tell us about the convexity of the problem. So I have an inclusion problem here, building from the minimization problem. I know this function is not differentiable. This is differentiable. Another property I need is the convexity. So if I have to drop this convexity, I want to build a similitude, and this takes me to this last inequality I have here. And from here, you could see this is an equivalent function. If you do some mathematics, you should be able to arrive at this from here. So what this is telling us is that if this function is convex, then this inequality will hold. And this inequality is what leads to monotonicity, which I'll define in the next slide, that the function is monotone if it satisfies this inequality. In other words, the function is monotone imply that the function is, I know I can build on the previous result from the optimization problem into this. And further into their algorithm, I can also apply the previous algorithm from the case of the optimization problem into the monotone inclusion problem. And a simple example of that is the fall backward method, which is the proximal gradient method. This can lead into what we have here. This is we call this the resolvent operator, being the proximal operator that was defined in this case, the proximal operator being defined here becomes the resolvent operator of the monotone operator, the resolvent of the monotone operator, sorry. So I'm just trying to make a better analysis now. Okay, let's leave the optimization. Let's come to monotone inclusion. And what I just did here is define that a function, if the set that is not differentiable, I can make it a maximum monotone. And as far as I have a point that is monotone, then I can build the fall backward splitting method from the previous proximal gradient method into this. And I'll still have the same result as what I have in the proximal gradient method. Aside that, we have other types of fall backward method. Here we have the fall backward forward method by Tseng, which says that this algorithm will always converge if I pick my step size lambda between this interval, that will always have this iteration converging to the solution. And we have several other of them, from the reflected fall backward to several of them that cannot be listed just here in the talk here. So all this is just telling us is that the idea of the monotone inclusion was formulated just from the optimization aspect by breaking down some of the properties of the function we are dealing with in optimization. So coming to variational inequality. So for the case of variational inequality, I continue from the inclusion problem and say that, okay, if in this case, I take a particular instance of this non-smooth function as the indicator function. Then I can define a new problem, which I call the variational inequality. And in this case, I use an operator T, which is a monotone, or in other words, I'm just trying to conserve two property. The first is the convexity of the function, and the second is the differentiability of the function. Because when you look at T here, T is nothing but just the gradient of F that I have here. So I'm trying to conserve those two properties, the differentiability and the grade and the convexity of the function. So I say the function is monotone and the function is in other words, just okay, I can call it a monotone operator. So I know with that I've conserved the differentiability of the convexity of the function. So its differentiability will come into play when it comes to the types of or when it comes to the modeling of the problem I want to deal with. So a simple algorithm for solving the variational inequality is the projection method, which converges weakly. Then we have the extra gradient method, which is an advancement of the projection method, which converges strongly based on some parameter. So this was introduced by Kovalevich some years ago, and he has proved that this converge to the solution of the problem. However, we have some problem. I think this is well known because we have two projections. This doesn't come for free. And also aside that, T here can be monotone. In this case here, this will only converge if T is strongly monotone. But in this case, this we can converge for T being monotone. So aside this extra gradient method, we have other types of extra gradients. We have the subgradient extra gradients up to purple extra gradient. They're all building on what we have here from one step to another, trying to modify some parameter. For example, the subgradient is trying to see if we could reduce the number of projections we have here from 2 to 1, as well as the descent as well is trying to see if we could reduce the number of projections from 2 to 1 and the number of evaluation of T as well. For both subgradient and descent, we have two evaluation of T, but for Maliski, we have of T at every iterate. No, I think that's for pop-off. For pop-off, we have only one evaluation of T at every iterate. So all these are just version of improvement on the types of extra gradient method that we have. So also a quick one is on the equilibrium problem. So we could formulate an equilibrium problem as a variational inequality by setting the function T of x comma 1 minus x to be equals to this function g, where g is a bifunction, which also have to satisfy some property. So yeah, this one was introduced by Brown Oakley and has been studied further ever since then. So we have several results going on in this aspect. And since these problems are being equivalent, we could always build from the knowledge of one to the other. So these are just building from the knowledge of variational inequality into extra gradient method. So we have building on that with several authors formulate several algorithms from the extra gradient as well as subgradient extra gradient and so on and so forth. Now, moving to the application aspects, we have the machine learning like we have here. How can we formulate or how does the machine learning comes into play in terms of this problem I've discussed about? So I take an example here, banknote authentication, where we try to we try to see if we could identify the banknotes in terms of being the fraud and the authentic one and the non-authentic banknotes. So we do some experiments on this, which falls into classification problem. We have the data set. I think I present an example of the data sets. Oh, sorry. Yeah, I present an example of the data set. So I'm still coming there. So we have the input fixtures, which are fixtures that are extracted from the banknotes. It can be the number, it could be the image, and a lot of many other features that are extracted from the data set. So, and as well as we have a binary number, either 0 or 1, which determine if a banknote is authentic or is a counterfeit. So, and then with this, we can select a model that would suit the problem that being considered. For example, I think for here I use variational inequality. So I have to suit a model that fits into variational inequality. So I will be able to apply variational inequality to solve the problem. So the data sets are widely available. These are some statistical terms I'll just trying to explain about logistic regression. So which in terms of reformulating back to variational inequality or formulating back to optimization problem. So when we have an optimization problem and we have a function here we are dealing with. So here, this function, as we could see, so here it's a differentiable function and convex in the same sense. So I could apply some of the knowledge I have from the previous slide to solve this particular optimization problem, building on what I've discussed earlier. And here as well as if I could try to like I'm considering the problem being the data set, trying to do some overfitting on the data set, as well I can add some regularization parameter or regularization term to this aspect here. And then here I will have a problem that it's not smooth because this part here is not smooth. Then I can use the composite function because I have the convex and the smooth part and the convex and non-smooth part. So I could use the proximal gradient idea to solve this particular problem, which is exactly what we use in this case. So so what I just try to do here is just try to break this down into how I use this for one of the experiments in my paper. So here I set my F to be the smooth part and G to be the non-smooth part, which align with what I have in the proximal gradient algorithm. So I have this paper on arXiv, so where we use a forward backward type algorithm to deal with some application in machine learning. And the first instance, we pick a data set containing 1,372 rows, the one on the banknotes. So we have this data set on open access. You could get it from UCI library. It contains 5 columns consisting of 4 features and 1 target class. The target class is a binary class which determines if a particular feature, if the particular node is counterfeit or it's authentic. So also the data set is balanced in the sense that we have a normal curve in terms of the ratio of the counterfeit to the ratio of the authentic nodes. It's just 55 to 45. So I use this for the experiment. I put a picture of the data set, how it looks like. It's just something here. What we have here. These are numbers that have been extracted by authors who are working basically on data sets. So they've extracted these and be able to classify this into authentic and non-authentic. And as well as we do some machine learning problem on this, trying to split the problem into testing and training. So to see we try to train the model on what we call the training data set. So I split this into 10 to 90. 90 is the training data set and 10% is the testing data set. So when you train on 90, we test on 10% and see if our algorithm can extract the features or can predict if a banknote is counterfeit or is authentic. So we tried this for 4 subsets, and we run some performance metrics to measure how the performance of this algorithm are. If they are in terms of its error, the mean absolute error, mean square error, root mean square error, as well as the prediction and the accurate score. We run all these. These algorithms we use, as you could see from here, this is just a form of forward backward algorithm. We have the forward case here and we have the backward case here. We added some parameter here just to try to accelerate the performance of the algorithm. And what's the result you obtain from here is that from what we have from our metric, our algorithm is algorithm 1 and 2. We observe that though we are able to reduce the time of its computation compared to other methods, the most popular is the ADMM, which is the standard and the most simple method. However, in terms of the error, we obtain a quite larger error than that of the ADMM, but lesser than some of the existing methods in the literature. So what this tells us is that though our method is, in terms of its time of performance, it has a positive result on that, but nevertheless, there is negativity in terms of the error or in terms of the prediction. It's not too much, it's not too accurate. So you have to try this as well. I think this for 10%, we tried the same thing for 20%, 30%, and so on and so forth. So a keynote from here we could take from here is that we're able to reduce the time of computation. However, the performance of the algorithm is not too effective to our liking. So we try another experiment. Apart from that, I think we use a 2 set as well, another little set that does not focus on the banknotes in the other case here. So that was unbounded. So everything you could obtain it from this from the article. I think is an archive, which means an open access article. I could not present everything here just to save time and for the sake of being precise what we'll be discussing today. So going further, just to wrap this up, we also discussed about, I also put something in image processing in one of my articles where I give application of optimization in image processing, especially on my research that I've been working on for the past years. So what we did here was in terms of image processing, you have an image. For example, you take picture, or when you take a picture of an image, definitely it will come with some noise. Or perhaps you send a signal, or it's definitely come with some noise. So you try to see if you could remove this noise from the original image or from the original signal. So that's all what image processing is all about. So we have the original image. We try to then with the addition of some noise via a linear mapping, and as well as we have the observed image, which is this big here. Everything here becomes a noisy image, as we will see in some of the experiments we have done so far. So just a brief discussion of the mathematics behind it. This problem that's formulated here in terms of its engineering can be discussed in its mathematics as solving this problem here. So here we have a convex and smooth function and a convex and non-smooth function. I use a regularization here because this norm can be in form of anything. It can be a TV norm, or it could be the norm 1 we all know, which is a normal regularization parameter in terms of norm 1. So that's why I just put a reg here. But what I just want to take note from here is, what I want us to take from here is that what we are solving is nothing but the problem I've discussed earlier. Formulating, I think here it's for image machine. Okay, it's also a monotone inclusion problem. So what we did was we formulated the problem for monotone inclusion from this model into a monotone inclusion problem. Then we apply our algorithm, which is this algorithm I have here. So we apply this algorithm to solve the image processing problem. How do we do that? I think that, I just come here to give the detail. Though this is also open access, or is an optimization. I think we also have this on archive. So I explain the process at which we try to reformulate this model from the image processing problem into an optimization problem, into the monotone inclusion problem I have here. And as we apply this algorithm to solve the problem we have at hand. Eventually, we considered, think 3 images. Here we have 2 images, paper and lighthouse. But I think in the paper we have 3 images. So these images are being read into MATLAB and do some mathematical experiments on that. We measure the performance of our algorithm with the signal to noise ratio, as well as the improvement in signal to noise ratio. And this can tell us how the performance of our algorithm is compared to others. And what we could take away from it is that, yeah, we have the original image, we have the corrupted image by adding some noise. We could reconstruct the original image, though not effectively, but at least better than other existing methods in the literature. We could reconstruct the original image with our algorithm. So the same thing we do for the lighthouse, as well as I think we have 3 images in the paper itself. So yeah, but yeah, I reported only 2. So we try for hours with some other existing method in literature. Yes, in our case, we're able to reduce the time for, I think, the lighthouse, but not for the purpose image. But the performance of our algorithm was more effective because here we have the higher the SNR ratio, the better the performance of the algorithm. So the performance we obtain from our algorithm is quite better than the performance of every other algorithm we compared with. So yeah, I think we have just 5 minutes to round up. So this is what we have done so far. What I'll just try to put out is what I've been doing in terms of the application of optimization in the real world. I'm not leaving that to the engineering now. I want to do it myself. And that's one of the beauty and one of my motivation that makes me to move a little bit from a fixed point into optimization. So make problem or as variational inequality, solving them with the available tools on optimization of remote inclusion of racial inequality. So this is something I've been doing, which I'm still open to. And I will also be happy if I have other people who are also willing to go in this trend of research, to also collaborate with people. Thank you very much, and I hope I'll be able to pass one or two messages today.
Thank you, Dr. Jolaoso. You really have given us a lot of lecture in this area of research. We want to appreciate you, and want to also appreciate your mentor, Prof. Oshinuga, that joined us. We are glad for the opportunity you've given to us to learn from you. And for all the participants, especially the PhD students, this is really an area you want to look at. You heard him. He said that, there are those aspects of application of fixed point theory in optimization, which have been issued, the engineers have done. Is no longer interested in leaving it to the engineer, so that he want to do that. And I want to encourage, especially young ones and many researchers that are here to go in that trend. So I want to appreciate everyone for joining a FANOG research group monthly meeting. I want to thank you, and maybe I want to give one or two person the opportunity to also give a vote of thanks to our speaker. I don't know if Taylor and Demille want to say something. You want to thank our presenter for the day. You can unmute yourself and give your vote of thanks.
Thank you, sir. Thank you, sir. Can I say something, sir?
Okay.
Thank you for your nice presentation.
Yes,
yeah. Thank you. Can I say something, sir?
We want to let's Taylor finish, then you can tell. Taylor, we are listening.
Yes.
Yeah, go ahead. Go ahead. Go ahead. Go ahead, Demille, Taylor. We are listening. Go ahead.
Thank you for your nice presentation. And that's all.
Okay, thank you. Thank you very much. Yeah. I don't know if there's any question. Just we have only 1 minute. Any question from anybody or comments?
Yes, yes, sir. Thank you, sir. I have one or two questions, sir.
Go ahead.
Okay, thank you. The first, let me first of all thank, because we don't have much time, let me thank the presenter. Very fantastic and a good job. Kudos to him. Secondly, I want to know when is the next meetings taking place, so that we can also keep to it.
Yes.
And the third.
Okay. Go ahead. Go ahead.
Then the third question, I have some questions for the presenter. I don't know, maybe you might not be able to address some of those things now because of time. Probably maybe he can give me his contact. I can reach out to him personally, because some of those questions, I don't know if the time will permit me to present some of them to us now.
I don't know,
Because
Dr. Jolaoso, can we come back maybe in the next 1 minute to
Yes, you
if
can come back.
so that we can
Yes, you can come back.
okay, we
Yeah,
can
we can come
rejoin.
back.
Can we rejoin
Yes,
to
yes.
take the questions?
okay,
Yes.
okay, sir. Okay, sir.
Okay, so what we do, I think in less than 30 seconds from now, the time will elapse. So we rejoin and then we take the questions. I think it's better we take the questions now.